Welcome back to this lecture on functions. In this fifth and last segment, I'm going to ask you to prove the following theorem. Theorem number 2 says a function that is increasing but not strictly increasing is not injective. So the goal of this exercise is twofold. First, I want you to get very comfortable with the terms increasing functions, strictly increasing functions, injective functions that we learned in this lecture. And two, I want you to practice writing proofs, which is one of the major learning outcomes of this course. So please stop the video and do your best to write the most complete and detailed proof for this theorem. Now remember, before writing any proof, you want to make sure you clearly understand the statement of the theorem. What this theorem states is that for any function f, if f is increasing but not strictly increasing, then f is not injective. In other words, we have a universally quantified statement over the set of functions, and that statement is a conditional. So, first we're going to pick an arbitrary domain and codomain as subsets of the real numbers, and then we're going to pick an arbitrary function f from D to C. And the most natural way to prove a conditional is to use a direct proof technique, which means we're going to assume the hypothesis of the conditional, namely that f is increasing and f is not strictly increasing. Notice the assumption in this case is a conjunction of two propositions. Now, if you did not set up your proof this way, why don't you stop the video and try to rewrite it with this starting point? Okay, so from here, we're supposed to prove that f is not injective. So the natural thing to do is to start from one of these assumptions and go ahead and infer something. So I'm actually going to start from the second assumption here, which is that f is not strictly increasing. So let me write down the definition of a function being strictly increasing here, and I'm going to precede that definition with a negation, since we assume that f is not strictly increasing. And now we can apply our knowledge of predicate logic to move the negation past the quantifiers towards the conditional. Remember what happens when you do that? The for all becomes there exist twice, and now the negation applies to the conditional. Remember how the conditional can be rewritten as a disjunction, like so. P implies Q is equivalent to not P or Q. Now we can use De Morgan's law for disjunction. So the negation of a disjunction is a conjunction of the negations. And here is the result. In other words, those two negations cancel out. And the negation of f of x strictly less than f of y is f of x greater than or equal to f of y. Don't forget the equal sign here. Now that we have an existentially quantified proposition, we can use existential instantiation twice to first drop there exists x, and we pick an arbitrary name we haven't seen before, like the constant a, to replace for x here and here, and then we apply existential instantiation again to drop there exists y, and now we must use a different name we haven't seen before. So let's say we pick the constant b to replace for y here and there. So after these two steps, we end up with the proposition that a is less than b for some values a and b of the domain, and f of a is greater than or equal to f of b. Now, since this conjunction is true, we can infer, I'm not going to write it down in this informal proof, that both this proposition is true and that proposition is true. And in particular, I'm going to use this proposition first together with the assumption that f is increasing, which we haven't used yet, to infer the fact that, so what can I infer? If b is greater than a and f is increasing, then it must be the case that f of b is greater than or equal to a. But this inequality, in conjunction with this one that we already established, together imply that f of a is equal to f of b. So what does that mean? Well, let's keep going. One thing we can infer from the fact that a is less than b is that a is different from b, obviously. And so now we can combine these two propositions to infer that a is different from b and f of a equals f of b, where a and b again are these two arbitrary constants in the universe. But since a and b exist, we can apply existential generalization twice to infer that then there must exist an x and there must exist a y in the domain such that x is different from y and f of x is equal to f of y. So we just established that there exist two elements of the domain x and y that are different, and yet they have the same image according to f. That by definition means that f is not injective. Now f was an arbitrary function, so now we can use universal generalization to conclude that for any domain and codomain C and function f defined over those domains, if f is increasing and f is not strictly increasing, then f cannot be injective. This concludes the proof of Theorem 2 and this first lecture on functions.